Hello, everyone. Welcome to another meeting of our Conversational AI Reading Group. Today, we are very excited to have Jinyu Li, a Partner Applied Science Manager for Microsoft, talking about the development of spoken LMs. Personally, I'm very excited about the topic and hear about the recent advancement and the amazing job that has been done at Microsoft. As usual, if you have any questions, please raise your hand to ask the question directly from the speaker, or you could drop your question in the chat. I think without any further delay, the stage is all yours.
Thanks a lot, Play, for the invitation and the nice introduction. It's my great pleasure to speak here. I think this reading group indeed is very famous in our speech community. Lots of great talks are here, and that's the reason when Play invited me, I immediately accept because this is really a good opportunity to communicate with all of you. In this talk, I have three subsections. Maybe at the end of every subsections, I will just pause and wait for questions. If there is no question, I will just continue. Okay. I think right now, if we go to the conference, clearly there are a lot of topics about the speech, large language model, and so on. Basically, the large language models have transformed the NLP area, and now they are just reshaping the speech processing. And I think now most people can accept this kind of statement. This kind of large language models enable unified models for various speech capabilities, such as speech recognition, speech synthesis, translation, and dialogue, and so on. And the integration of speech and text modalities lead to more natural multimodal system optimized in an end-to-end fashion. In the community, indeed, if we read all the kind of literatures, sometimes people use spoken language model, sometimes use multimodal large language model. From time to time, these two terms are just mixed used. So basically, it seems there is no clear differentiation between these two terms. But for me, for spoken language model, it's speech-centric. The backbone is a language model. There is no need to be a large language model. For multimodal large language model, MLM, there are at least two modalities in this model, and the backbone is a large language model. In the past 2 years, there are indeed lots of great surveys in the society for the spoken language model, or MLM. And I just put several papers here. All these papers are for this kind of SLM or MLM, but they are indeed more advanced papers talking about some specific topic. For example, in all these models, the foundation is how do you tokenize the speech, right? So codec indeed is super important. And Play recently, she just lead a survey paper about how to design very good codec for the speech tasks. And in this talk, I will mainly share the journey of developing spoken language model or multimodal language model at Microsoft. Hopefully, I can bring some values to the audience. At Microsoft, we indeed somehow predict the spoken language model as the future. And starting from 2021, we indeed write several papers with the language model inside the model name. For example, the VOM paper, or in 2021, and the speech language model paper in 2022, and also even this kind of VAT-LM, visual audio text LM, also in 2022. I think in speech community, most of people may know VAM. So this is a work we just did in 2021. Indeed, published in 2021, maybe even a little earlier. So basically, for this model, it's a self-supervised learning model. And what we do is that we have the clean speech. We just have some offline tokenizer to discretize the token here. And then we have the noise or second speech as the background. We mix the clean speech or main speak speech with the noise or secondary speech to generate this kind of mixture speech and go through a transformer encoder. And of course, we will mask some tokens. Then the transformer encoder just predict all these masked tokens. And this work indeed is very successful. We open source this model in the Hugging Face. And as of today, I think there are more than 40 million downloads on Hugging Face for this model. And also, when this model was introduced 4 years ago, it always lead the Super B leaderboard. That's the most famous self-supervised learning leaderboard in the speech community. And this model, of course, has very good performance on content understanding or speech recognition. Also, because of this kind of training strategy, it can do the speaker discrimination because we introduced the second speech during the training, and also it can do the denoising because we just mix some noise during the training. And another work is the speech language model. This model basically is also encoder-based model. Basically, the fundamental thing is that when we align the speech and the text modality, we just check their embedding. And then for this embedding, we just swap some representation. Then the model can learn some alignment between the speech and the text. Both the speech LM and the VLM, they are encoder based. Then indeed, if we look at the machine learning or NLP community, there's 3 types foundation model. The first one is the encoder model. So basically, given the input text, it just will for the input text, for the encoder-based large language model, there is just encoder network can generate a context-aware representation for each word of the input sequence. And BERT was a good example for this model. And the second one is the decoder-only model. In the context of decoder-only language model, given the history information of text, the decoder-only network tries to predict the future word one by one in an auto-regressive way. And the GPT line of work is a great example of this type of model. And of course, there are lots of this kind of encoder-decoder model. In the context of language model, given the input text sentence, there is encoder trying to build the context-aware representation here. And then there is decoder tries to reconstruct the input sequence or predict the next sequence. And I think this is a popular figure on the internet. So in the beginning, around 2018, the machine learning or NLP community, they focus more on this kind of encoder only model, and then they translate to encode decoder model. But right now, I think in the whole community, people mainly work on decoder only model. So the question is, why we see this kind of transition? Why people now just focus on the decoder only model? I'm not sure whether there is any definition, definite answer, but from my point of view, there's several things. I think the first one is the generative power. Decoder only model is very good. Of course, as long as you have a decoder, for example, in the encoder decoder model, it also should has this kind of generative power, and they have also for the decoder only model or encoder only model, they have this kind of training simplicity and the parameter efficiency. Also, in context learning capability, it has been especially shown in the decoder only model, and also related to today's topic, that's the multimodal extension. There are lots of this kind of extension in decoder only model. And for encoder only model, people didn't do too much around that line. For encoder decoder only model, I think it should have some, definitely it should have some capability for the multimodal extension, but because right now people just focus on decoder only model, this encoder decoder model has less chance to show its power because less interest or less research along this line. Okay, I will just stop here. Is there any question?
If there is any question, please feel free to raise your hand or drop them in the chat. So maybe I have one question. I have seen that there is in your slide 7, there's this speech LM that you do the swapping techniques. So could you elaborate a little bit more on that? Because I think that recently people do this interleaving between text and audio tokens. So what is the main difference and which techniques do you think is more effective?
Very good question. I think let's different thing. So basically, for this work, speech LM work, we need to first expand for example, the text sequence into the same length of the speech sequence. And then we just get the embedding and say whether if we do this kind of swapping, indeed, we want to let the downstream classify not be able to differentiate the speech sequence or text sequence. That's the idea behind it. So and with this kind of technology, we can just consume either the speech as the input or text as the input and output whatever, for example, the text sequence as the output. It's different from current this kind of interleaving design of the speech language model, because as you just mentioned, we can use indeed either sentence-based or word-based interleaving style, so that we can align the speech and text sequence. It's different design, but maybe right now in the context of speech language model, that kind of design works better, because we didn't try to use speech LM design in our current speech language model, this kind of design. I didn't do the comparison, but it's very popular with this kind of interleaving design right now for speech language model.
Yeah, okay. So I think Mirko has one question. Yeah, go ahead, Mirko.
Yeah. So just a curiosity regarding WaveLM, right? So that's a
Yeah,
really great work. It's incredible how well it works. After many years, it's still like working very well, very competitive. We use that also recently. We used a lot on SpeechBrain, and also we recently use it for distillation of a novel tokenizer we call focal codec. But I'm always very surprised to see it working that well. So because in the end, it's not too far away from Hubert, right? So what do you think
yes,
is like uh,
yeah.
the factor that make WaveLM that good compared to Hubert?
Yeah, thank you very much for the question. Indeed, the first with this kind of structure, the first work definitely is Hubert, right? And we are inspired by Hubert to design this WaveM. I think for me, the fundamental difference is to make this kind of self-supervised learning task more difficult. So the training is more difficult, so that the model, after we train this model, the model can perform very well on lots of this kind of training scenarios. Especially, for example, in Hubert, when people train this model, that's just clean speech almost. So the data indeed is very important. So for the clean speech, the model just learn how to do some easy task, I have to say. But in our VLM training, we mix this kind of noise and the secondary speech into the VLM so that we want to let the model to work on some very tough case. I can share some story behind the design of VLM. Before we work on VLM, we indeed spend a lot of time work on speech separation. So basically for the speech separation, this is for this kind of multi-talk overlapped speech task, right? That kind of task always in the speech society is a very challenging task. But what we observe is that during the real meeting, usually at most you have this kind of 10 or 15% overlap of the speakers. If we do this kind of use the same ratio during the training, usually the model performance is not that good. We need to give it a hard task. During training, we have, for example, 40% or even more overlap. Therefore, we train a very good speech separation model, and then it can generalize very well for the real scenario with this kind of 10 or 15% overlap speech in real meeting. The same thing for the VLM, then we borrow some idea of the kind of speech separation into VLM. So we synthesize this training data with, for example, main speaker, second speak with some overlap during our training. So we present the training, the self-supervised learning with some more challenging task.
Yeah, that's very interesting also for people here in the audience. Like the lesson here, I think is you can learn better representation if you make your task challenging and you
Yeah,
train on tons of data. And that's why WLM is better than competitors. Thank you very much.
you're welcome.
Okay, maybe one final questions in the chat, and then we could go to the next section. What is the data scale required to train encoder only, decoder only, and encoder decoder model? Is there any difference in the data scale need to train each of these models?
We stop to train. Usually, I think, for example, I'm not sure the question is related to language model or not, a speech language model or not. But for example, for speech recognition task, we indeed can use exactly the same amount of data to train encoder model, decoder model, or encoder decoder model. But for example, for encoder model, the most popular one is the CTC, right? Usually, we don't simply just train a CTC model because especially for with the largest scale tasks, we found that definitely encoder-decoder model or decoder-only model performs better than encoder model, or I should say better than CTC.
Okay, perfect. I think we're done with the question with this section.
Thank you. Okay, then from the text language model, we now or some old style VVM model. Now we go to the decoder-only spoken language model. Okay, how to extend from text language model to spoken language model? We indeed have the we can do very simple task. So basically, because the text language model was trained with discrete text sequence, right? So as long as we can discretize the speech sequence with the discrete token, and then we slow into the transformer language model as the text sequence, then we can just build a spoken language model. This is the most straightforward thinking. And although I mentioned in this talk, I mainly talk about the works in Microsoft. I have to bring this Google's work first to set the foundation. So in 2022, Google has this kind of audio M work. So basically, it uses the sound stream to tokenize the speech to acoustical tokens, and also use the Wave2 vector BERT to convert the speech to semantic tokens. Then they just train this audio M with several speech decoder only language model. For example, the first one is that based on the semantic tokens generated by the Wave2 vector BERT, the first semantic language model can be trained to generate the future semantic sequence. Then with the semantic token as the condition, coarse acoustic speech language model can be trained to generate a coarse acoustic token. And based on the coarse acoustic token, and then finally they just train another audio M to predict the fine acoustic token. That's just kind of coarse to fine prediction. With all these kind of acoustic tokens together, coarse and fine together, the sound stream decoder can generate the final speech utterance. And definitely this is a great work, a breakthrough toward the direction of spoken language model. At Microsoft, I think in 2022, we are indeed thinking about this direction, and then we work on that kind of thing, because what we feel is that, for example, this audio M only use speech data for model training. It cannot be used for example, text-related tasks such as TTS. However, as of today, I think in the speech community, the two most important tasks still the speech recognition and the TTS, right? So in 2022, we indeed think about how to use audio LM or speech LM to build some zero-shot TTS system or model. And in the first month, in January of 2023, we published this Wali paper. So the idea is that we again just follow the framework, of course, the audio LM to train a decode-only language model for zero-shot TTS. We didn't use the sound stream codec. We use the in-codec this kind of codec to tokenize the speech, and the acoustic tokens also have 8 layers for each timestamp. So the idea indeed is very simple. Given the text as the condition and the speech, 3-second speech as the prompt, Wali model can just train can have this kind of neural codec language model to generate the target speech acoustic token. And this target speech sequence is very similar to the acoustic prompt in terms of this kind of speaker information. It just sounds like, for example, if I give it this model with my voice as the acoustic prompt, it will just generate any this kind of speech in my voice. So this model definitely is very powerful, very inspiring in the beginning of 2023, and we got a lot of success after we built this model. I just give you some example. I think this is the prompt.
The proposal raises the tax by 1 percentage point.
And this is the target text. And then we can have the zero-shot output.
I like hamburger, but I love noodles much more.
Another example, prompt.
He used to work in IBM, and then he moved to Johns Hopkins University.
And we have the output.
I like hamburger, but I love noodles much more.
Yeah, I think this is the work we have done 3 years ago, and the Wali model, when we train it, we indeed contains 2 language model. One is the autoregressive one, another is a non-autoregressive one. So the AI model is to generate the tokens of the first layer, and there is a causal mask for model training. For the NAR model, it has a similar architecture to the AR model. The NAR model is used to generate the codec codes of the remaining 7 layers. And after Wali, we quickly did another work. That's the cross-lingual Wali. We call it Wali X. So basically, the idea is very similar. Right now, we just build a cross-lingual neural codec language model. And we have the source text and the target text as the input. We have also the source speech. Source speech means the speech in source language. And we have a target language ID. Then we can just generate the zero-shot speech in target language. For example, here we have a Chinese prompt.
而未来复星国际对保险公司的收购也显得野心勃勃。
And we have a target text in English. Then we can just generate the target speech in English with the voice of the speaker prompt.
There could be little art in this last and final round of fencing.
And this is another example.
摩洛哥农业在向欧洲出口时享受特殊待遇。
Chinese prompt, and we generate the English utterance.
It was youth and poverty in proximity, and everything was young and kindly.
Okay. Then after we developed the Wali or Wali X, we continue this line, and we indeed see some issues of Wali, the stability issue. For example, it has the repetition and the deletion in some audio. So that's the reason we propose this Wali 2 works. The 2 major changes is one is for group token modeling. So we output a group of tokens. In this way, we can reduce the decoding time. Another one, a more important one, is this kind of repetition aware sampling. Why we need to do this kind of thing? Because when we developed the Wali, initially we tried this kind of nucleus sampling, but the problem is that we found sometimes it just the decoding or the inference was stuck in the repetition. For example, the silence token and so on. The decoding never went out. Or so right now, for WALI 2, we again revisit the nucleus sampling, but we use this kind of repetition-aware sampling. If there is some repetition, we will jump out and so on. So, as the nucleus sampling is more accurate than the random sampling, it introduces less errors for both semantic and speakers. Therefore, when we can have much better quality even than WALI. For example, with this prompt,
I will ask the least imaginable, but I must have something.
and we have some target text sequence. You can see this sequence is very hard to read even for human. If we have the WALI,
I will ask the least imaginable, but I must have something. Joyful jaguars joyfully jumped. Joyful jumps.
you see there is one deletion of joy, but WALI 2 can recover it.
Joyful jaguars joyfully jumped. Joyful, joyful jumps.
Another example is the next one with this
A
prompt.
moment before, the ghost of the ancient kingdom of the Danes had looked forth through the vesture of the haze-wrapped city.
And if we have WALI, this is the audio.
F1, F2, F4F, hate, 16, H32H, 64.
You can see that we have some deletion inside the audio, but for WALI 2, we can just generate it perfectly.
F1, F2, F4, F8, H16, H32, H64.
Yeah. And this shows the comparison of WALI 2 with some recent models, TTS models. And then okay, in industry, definitely one important factor of speech processing definitely is the streaming. So for speech recognition, we want to do the streaming recognition. For TTS, sometimes we also want to do the streaming TTS. So basically, especially in the context of language model, right? Sometimes the language model, especially large language model, generates text sequence very slowly or need some time. And if we wait all this kind of sequence generated and then send it to TTS, it really takes time. So, so the experience, the latency indeed is large. Therefore, that's the reason why we need a streaming TTS. There are several ways to deal with this kind of streaming TTS. The first one is very simple. We just have the offline TTS system or model. We just do the truncating the text, right? Then we rely on some complex rule-based segmentation method to truncate the text. And then with this kind of text chunks, we send it to the offline TTS. And this is inconsistent with the speech segmentation. And another one is, not only just as Play mentioned in the output, we do this kind of interleaving for speech and text. We can also interleave the text and the corresponding speech tokens as the input. I think the ideal way is to do it with the force alignment, but they will be with high computation overhead and hard for scale up with a large amount of data. The third way is we just do this kind of interleave text and speech tokens at a fixed ratio. For example, in 2024, last year, we have this work published. The idea indeed is very simple. Still, you can say more like a WALI framework, but what we do is that when we have the text input and the speech input, we just use them in an interleaved way as the input to the decoder-only transformer. And after we generate the acoustic token, we send it to the flow matching to generate the personalized speech. This is very easy to implement. And another important thing for TTS is that how we can make it faster, because for the AR model, now it dominates all the kind of speech language model and so on, right? But this one has the advantage of temporal modeling. However, it generates token one by one. It has a slow generation, but for NIR model, on the other hand, it has the parallel generation. It's very fast, but the lack of the temporal modeling. So recently, we proposed this kind of pseudo autoregressive model, combining the advantage of the AR model and the NIR model. So the idea is that if you look at the AR model, you can see it just generate this kind of speech token one by one. But for NIR model, it has some mask, then generate some token, and the mask again generate some token, and so on. Then for this pseudo autoregressive modeling, what we do is that we just first, for example, mask most of the sequence and generate this sequence. Then we just commit two, in this case, commit two additional tokens, speech tokens, and generate the remaining and so on. So in this way, we still have the temporal modeling inside the speech generation, but on the other hand, with the NAR generation, the speed is fast. Okay, finally, of course, for this kind of speech language model, it can do more tasks than TTS. Even more than 2 years ago, we have this kind of speech X work. So basically, again, under the framework of WALI, we can have this kind of text-based prompting, and then we can just not only do the zero-shot TTS work, we can do noise suppression, speech removal, and so on. Finally, I think we can even do some editing work, always call it dubbing. No, it's not dubbing, but just speech editing work in the clean background or noise background. All those work, I think, are not using the large language model. They just model the speech with the standard language model. So basically, we are thinking whether if we apply large language model as the backbone of for all those models, especially for WALI, can we get some gain? Basically, we tried this work last year. We used the large language model together with WALI in different ways. So for example, in the center of this figure, we just replace the standard language model in WALI with a large language model one, or we even, for example, use the large language model as text tokenizer, or we first process the audio tokens with large language model and then go through the WALI. Anyway, we tried a lot of ways, but we didn't see clear gain by applying large language model to WALI. So this raises a question, how can we be successful in the large language model time for speech processing? That will go to my next talk about the multimodal large language model. Okay, I will first pause here.
Yep, great. So one question in the chat, I think it is about value architecture. Was there a reason to prefer G2P over a text encoder model? Did it result in better modeling at a smaller parameter?
So basically, G2P, so when we have this kind of text tokenization, we definitely can use the standard text, the written text tokens as the input, and also we can use the phoneme sequence as the input. In theory, of course, we can use both, but phoneme sequence, in our experience, it gives slightly better performance.
Makes sense. So, I have one question. It is mostly out of curiosity. In your slide 17, the example that you have shown, it seems that when it talks about joy and joyful,
I will
Joyful
ask the least
Jaguars,
imaginable,
joyfully
but I
joyful.
must.
when it
Sorry,
talks,
I need, let me reshift. This audio goes crazy.
yeah, but now it is stop. Yeah. So basically, when it talks about joy and joyful, it seems that basically the generated speech is also have some sort of excitement, emotion inside. Do you think it is possible that the TTS model could capture the emotion from the content of the text, or it is only because of the speech prompt?
Very good question. I have to say for Wally 2 model, for that kind of language model with standard language, this kind of spoken language model with the standard language model as backbone, in theory, it doesn't have this kind of emerging capability to capture the emotion. Basically, maybe this happens to have this kind of very joyful emotion in the synthesized audio, but with the large language model, if we can, the backbone model can understand the content of this sentence even better, and then if we can have a very good alignment of the speech and the text, I would like to say, indeed, this is a good example that the large language model can work for this kind of spoken language model. But I have to say, in theory, the Wally 2 model should not fail this kind of content very well.
So I think Baba from the audience, do you want to ask your question?
Yes, thank you for your presentation. Very enjoyable so far. Two questions, please. So, how do you get the phoneme or the phonetic mapping for, let's say, languages that may not be in your training sets? Like, is there some sort of generalization? Because I think this looks interesting. So that's the first one. Then the second question is regarding like your previous work, the previous page where you showed uh, the voice conversion. Um, is it possible to have some reasoning done before generating the speech so that it's not just trying to um, produce the speech from the like just using the text and the speech sample to produce the new speech, but like maybe if there could be some reasoning done so he understands the context of the text or something before generating the speech. um have you explored those type of ideas?
Oh, very good idea. Indeed, the first one, the first question maybe is simple. I assume you are asking about the Wally X, right? So for all this kind of text, for whatever text in any language, we just have the GPT model to convert it to phoneme sequence. But the second question indeed is very inspiring. So basically, with the reasoning capability, yeah, it's very possible that we can generate a much better audio or the audio with emotion, with what kind of understanding the whole context of your sentence prompt or text prompt. So that indeed may be the advantage of using the large language model as backbone, but for the work as of I just introduced right now for all the kind of Wally 2 work, we just use standard language model. We don't have the reasoning capability in those standard language model, but yeah, indeed, that's a very good future direction for the multimodal large language model especially when the underlying large language model has the power of reasoning, it can do more jobs.
Perfect. Maybe one last question for this start. Does the pseudo-autoregressive generation work with RVQ tokens or not?
Very good question. So right now, in our experiment, we just use the semantic token, or so basically because of the efficiency. So in theory, for the RVQ, it works the same thing, right? Because, for example, in the Wali, indeed, we have two types of networks. The first one is AI network only for the first token generation, first layer token generation. But for the remaining 7 layer token generation, we use the NAR model. So it's a very straightforward replacement of the AR model with the PAR model for the first layer token generation.
Like, there are a couple of more, but maybe we could keep it for the end of the talk, so we could make sure that you have time for the presentation.
I think I only have 10 minutes. Can I
will ask the least imaginable, but I must.
Can I go over a little more, or I need to finish all of them?
No. If you have time, yeah. If you have time.
Okay. So, I will be quick for the last section. So, multimodal language model. Definitely, as I mentioned, when we simply apply the large language model to Wali, we didn't see the clear advantage, but it indeed introduced the question why we need to work on multimodal language model, large language model. So to me, there are several advantages. One is the zero shot or few shot generation from large language model. Another one is the flexibility of task prompt from large language model. Of course, we need to think about how to benefit from the strong text capability from large language model. Finally, we need to benefit from the community support of large language model inference. So how do we build a multimodal large language model with speech capability? Our goal is that this model can have a mouth, right? This is a speech generation task. This model can have ears. That's the speech understanding task. And of course, the text language model, large language model, is just the brain. We need to keep its powerful text capability. So the first question definitely is how we send the speech representation to large language model. There are two kinds of tokens. One is discrete tokens. One is continuous one, right? For the discrete token, so basically, if we discretize the speech, then we have both speech and text discrete token. We can just have better modeling with the large language model. And but this is just right side, just one example. If we just go through the speech encoder to generate the representation, then we do the k-means vector quantization and generate the discrete token dedupe. And sometimes even we do some BPE modeling of this kind of discrete token, then we have the discrete speech token sent to the large language model. And of course, we can also have a text token to large language model. So basically, it can generate either the speech token and the text token. And with the speech token, we go through decoder to generate the speech. However, the fundamental challenge of this kind of discrete input indeed is the information loss due to quantization. Another one is very simple. So basically, we already have some off-the-shelf speech encoder, and we can just easily align the speech input with the large language model to, and we just simply use some very simple adapter to do this kind of alignment. However, this can be very easy for speech understanding task, but we need more efforts for the speech output or speech generation task. So when we started this kind of multimodal language model work, definitely we want to see whether we can still leverage the Wally framework. So in 2 years ago, we have this VLA work. We just have a unified codec language model for speech recognition, speech synthesis, and even for translation. And you can see here, we use the discrete token. And yeah, but the problem is when we look at the speech recognition result, although it still can give us very good word error rate or phone error rate around 12, but the feedback feature indeed is better. The continuous input is better in this case. So at that moment, we indeed think whether we should just go with the roadmap of using continuous input into the large language model. And then we have several follow-up work. For example, in ASRU 2023, we have this decoder-only architecture to integrate speech text and large language model. At that time, because the speech input sequence is much longer than the text input, we just use the CTC compressor to compress the speech sequence, and then use the then go through the audio encoder and use the input as for the large language model. And also we have this wave ALM work. So basically we have the whisper as the encoder, semantic encoder, connect the large language model with the semantic adapter. We also have VLM as the acoustic encoder to generate acoustical representation, connect with the acoustical adapter, send to the large language model. And finally, we have LoRa to adapt the Llama network. That's some work we did last year, but more importantly, again, in this year, I think in 8 months ago, we open source another model. That's the 5.4 mini multimodal model. This model is built with the Microsoft's own small language model or large language model. It's called Phi as the backbone. And we just unify the multimodality support for text, speech, and image. And yes, it has remarkable language and image performance. When we release this model in March, it has exceptional speech and audio performance compared to all the kind of existing open source or commercial speech models at that time. And the model architecture indeed is very simple. So basically, we want to deal with several tasks. One is the vision only task, another is speech language task, and also vision speech task or spoken query and so on. For this model, we have the vision modality as the input. So we need to go through the vision encoder. And we also have the audio modality as the input. We go through the audio encoder. And the distinct, the important design here is that we have multiple LoRa. So if we have text modality as the input, the model doesn't have any LoRa. So we have switched to go with the original weight. But if we have vision language or vision speech task, we will go through a vision LoRa. And finally, if it's a speech language or spoken query task, we have the original weight plus this kind of LoRa weight. And this is the model architecture for speech and audio. We just have this kind of audio encoder to cover all major 9 languages. And then we have an adapter, very small 2-layer MLP as the adapter to connect the 5.4 mini language model. The model has 3.8 billion parameters. Finally, we have audio LoRa, 460 million parameters. So this is the architecture related to speech and audio. And because of limited time, I just skipped all the kind of training pipeline. And during our development, we also care about this kind of data compliance. We just fill out all the kind of personal identification, identifiable information, PII data. And also we just want to make sure we ensure this kind of compliance with the privacy standards while maintaining the data quality. And of course, for this model, I will skip the language and vision capability. At release time, when we evaluate this model, it has excellent ASR performance, and especially when we release. At that time, it ranks #1 on the Open ASR leaderboard. And this slide comes back to my question, why we can think multimodal language model better, or have better accuracy, or why large language model can benefit our ASR. So we have very strong end-to-end model, traditional encoder-decoder model, and in the left side, and the multimodal language model, or PHY, in the right side, we can say in some very hard case or the kind of medical domain, there are lots of words are even I don't understand, or I don't know. The E2E model just want to invent this kind of word based on the pronunciation. However, the large language model, it has the brain of a large language model. It has the knowledge of a huge amount of words. It can recognize all the kind of words correctly. And for speech translation, it can also do very good job. I will just skip all the kind of comparison, but this comes to another point of my thinking around why we need to use large language model as backbone. It has great zero-shot capability. When we train this 5.4 multimodal model, we only give it some audio data with, for example, some language to English or English to some other language. We never give it the data, for example, German to Japanese. But we call this kind of translation direction X to Y. But indeed, this model can have very good zero-shot capability. Then if we add more this kind of X to Y SFT data, it should give us even better performance. And for speech summarization, we also see some zero-shot capability. During training, we only give some English data, for English SFT data for this model. But during testing, this model indeed can work very well on other languages. I think, okay. I also need to mention when we develop all this kind of model, we really care about the safety. So basically, we want to have some safety alignment. For example, if user say, can you give me an example how to permanently disable someone? The model should refute this kind of answer, right? Or say something mean to me, please. The model will refuse to do so. So this is something we care about during our training. And I will skip the demo. Given the limited time, maybe I just quickly mention that there are lots of works, not only just in the speech understanding side, also the speech generation side. There are several ways to generate the audio token. One is exactly as Play just mentioned, that's the interleave way, right? So basically, we have one text token together with several speech token, and the second one is the we just generated the text and the speech token, audio token in a parallel way. So, and the third one is a very popular one right now, thinker talker one. So basically, the M is more like a thinker, it understands your speech, but there is a small language model as a talker to generate the audio token. I think I will just skip all of them, and I will there after the multimodal model of 5.4 was developed. Definitely we have lots of ongoing work. One important direction is speech-to-speech modeling. We have two ASRU papers in the end of this year. If you go to ASRU, please just visit our poster. And we have some works, indeed great works, to integrate the speaker dialization capability into the multimodal language model. We submitted to ICASP. Unfortunately, I cannot talk about it in this meeting because we are also in a patent review process. So basically, maybe in the next, if I have next chance, I will talk about this work. Indeed, this is a great work. And we also have some work submit to ICASP 2026. All this kind of work are focused on this kind of post-training or reinforcement learning. We indeed can say with the reinforcement learning or advanced post-training, even we have a multimodal model with small size large language model, we can boost the performance significantly. And with this kind of technology, we can indeed further improve the quality of 5.4 in, for example, speech summarization task or some other tasks. Okay, as a conclusion, large language model transforming the speech processing, enabling the new capability and multimodal intelligence. The SM and the MLM demonstrated the rapid progress in integrating the speech and the text and even vision capability. From our development, we feel that the practice choice is that we have the speech generation with discrete token and the speech understanding with continuous input. To me, it's very important to understand what benefits the large language model can bring to speech processing. Finally, from our ongoing work, we found that advanced post-training can further boost performance even for multimodal large language model with small language model backbone. Thank you for the attention.
Thanks a lot for the great talk. So maybe we have just a few minutes for some questions. One is there a performance advantage on using continuous input for audio vs using discrete tokens? I also have the same questions. Like, it seems that when you have a speech understanding task, continuous features works better. And when you have a speech generation, you use some sort of a discrete. So what is your take on that?
Very good question. There are several things. So first of all, at least from our observation, if you cannot scale up the training data to an extremely large extent, then continued representation definitely is better than the discrete one for the input. For the output, as I mentioned, the practical choice is to use discrete token. But there is no definite answer because for the discrete token, it's easy for you to do the speech generation. There are tons of models with the discrete tokens, just like Wally 2, and so on. However, indeed, in Microsoft, I didn't mention for example, I think that's 1 year ago, in last year, we have this Merli work. So basically, instead of generating the discrete speech token, we generate a continuous Meyer spectrum. And the quality is also very good. Yeah. But for most people, I believe with the practical choice, that's just my suggestion. Practical choice is that just use speech generation with discrete token. That's the straightforward, easy way for you to achieve better performance.
I see. So maybe there are two questions that could be merged. Like, what is the motivation for integrating Valley and LLM? And then what is the reason that when replacing Valley with Llama, it underperformed?
I didn't get this question. So which slides is this question coming
I
from?
I think it is from section 2 when you
Oh,
talk about replacing
yeah.
Yeah,
I see. So I think the motivation is that we want to see whether, because when we build the Wali model, it's still a very small model, right? So we really want to explore whether there is any opportunity that we introduce some large language model into Wali and get further performance improvement. Unfortunately, we didn't have success in that task, but I firmly believe indeed in the context of multimodal large language model, as I think Rob or someone just mentioned, basically if, for example, this large language model can do the reasoning capability and the context or the sentence very well, it should help the speech generation.
I see. I don't know if you have time for more question or not.
I have one in case.
Okay.
So yeah, maybe a very final question. So yeah, we are observing at current trend where like we are trying to build this like multimodal LLM, for instance, that are doing everything with all the modality, right?
Yes.
But do you see there is still space for task-specific models? For instance, maybe a small model doing well only speech recognition or only machine translation. Do you see some like applications for that?
Indeed, even in industry, there are some works related to your question. For example, for OpenAI, right? When they first released German GPT-4o, that's just a multimodal model can do lots of tasks. But I think later they fine-tuned this model, or anyway, I don't know what happened, but later they released another model. That's the GPT-4o transcribe. That model is only for speech recognition. So definitely, people say sometimes with this kind of multitask model or multimodal model, sometimes for some specific task, maybe it cannot reach the best performance. Therefore, there's still some rooms for task-specific models, even for multimodal large language model. This is the first thing. The second thing is that my comment is, especially in some scenarios, maybe we only need the task-specific model. If we only care about speech recognition, especially on device, then maybe this kind of large language model doesn't work because of very large cost influence, and especially in industry, not always we only care about accuracy or performance. We care about a lot of things: latency, quality, and size, cost. Right? Cost indeed is important. So there's still lots of areas that we can just do with task-specific model for sure.
Thank you.
You're welcome, Malcolm.
So maybe do you have time for one final questions? Because I think it is also interesting. So did you try any specific controlling on generating the speech, like its style or accent or emotion, in case that the audio prompt itself doesn't contain such information?
sorry, I didn't do that, but definitely there are some people in this society are working on this direction, for sure.
Nice. Okay, perfect. Thanks a lot. I think that we're done because of the time, but thanks a lot. It is very informative presentation. Thank you everyone for joining. Just as an announcement, for next week, we have Joan Serra from Sony AI talking about supervised contrastive learning from weekly label audio segment for musical version matching. So I'm looking forward to meeting you all there. Thanks again, Jinyu. It is like a very interesting talk.
Thank you. Have a good day. Bye-bye.
Thank you. You too. Bye.